Hello everybody, my name is Stephen and today I'll present expressive density models for high energy physics using a custom latent space on behalf of myself and Darren Price. So in short, this work presents a method which projects data onto a latent space and then models its density. The method is useful when you want to create a statistical model with an arbitrary number of correlated observables for which the distributions are deformed under external parameter variations. And these observables may have hard physical boundaries. And also by sampling this model, we provide a stochastic generator, which is an alternative to the more commonly used GANs and VAEs. So what are the advantages of this method in particular? Firstly, it's designed to capture datasets with the above properties, which are common within the physical sciences. Secondly, it's easy to implement and easy to add additional observables to extend the model. And finally, if the initial out-of-the-box modeling needs to be improved, there are several intuitive ways for fine-tuning. So the key idea behind the method is this projection onto a latent space, and we show an example here. So the red histogram on the left-hand side shows the probability distribution over some observable x, which has hard boundaries at plus and minus pi. And the blue histogram on the right-hand side then shows the probability distribution after the projection. Firstly, we note that the hard boundary in x has been transformed into a smooth turnoff in u, which is easier to model. And the second and main purpose of the projection is to create a distribution which is well modeled by a mixture of narrow Gaussian modes, as shown on the right-hand side. And this is the same data as in the blue histogram previously, but now it's been fit with a Gaussian mixture model. And the real power of this method is that we can deform the distribution simply by modifying the parameters of the Gaussian modes local to the deformation. And by modeling these parameters using neural networks, we can capture the dependence on both other observables and on external parameters of interest. Okay, so how is this projection performed? Firstly, we construct a response curve over the space of the data. This is defined as a mixture between the cumulative distribution function of the data, shown here in red, and a simple linear response curve, where the fraction of each is controlled by some hyperparameter f. Secondly, we construct a response curve over the latent space, shown in the middle in blue, and this is defined as the cumulative distribution function for some arbitrary target distribution, shown on the right-hand side in purple. Now, this target distribution is designed to have two properties. Firstly, it has smooth edges to remove hard physical boundaries, and secondly, it's very flat in the middle, and this encourages the resulting latent distribution to be well described by many narrow Gaussian modes, instead of being dominated by a single Gaussian, as this would make it difficult to parameterize any deformations later on. So when designing this projection for your own observables, you only really have one choice to make, which is the value of the hyperparameter f. And the idea is that you initially pick a value which ensures that the response curve is not too flat, as this will collapse wide regions of x into a very narrow region of u. Then you can tune f to find a value for which the latent distribution is well described by the Gaussian mixture model. And when performing such a tuning, the intuition you use is that an f value close to 1 will make the latent distribution close to the target distribution, and an f close to 0 will make it resemble the data distribution. And if this still does not model as well as you require, you have the ability to change the target distribution or change the ordering of the observables in the autoregressive model. So as a demonstration of this method, we test it on an example within particle physics. Here we have 4 observables and we're looking at the heat maps of the 2D projections. On the left-hand side, we show the ground truth, which comes from simulation, and on the right-hand side, we show samples from our trained model. And you can see that we have captured the observable correlations very well. Secondly, this model has dependence on one external parameter, and as we scan this parameter by moving vertically down this plot, we see how the 4 observables are deformed. Now 3 of them remain unchanged. However, the third observable shows a very clear oscillating behavior, which increases as a function of the external parameter. And we find that the density model has done a very good job of capturing this dependence. So we conclude that the model could be used to perform hypothesis testing and parameter estimation on this space.